for each node in the graph, which comes out of finite element problems. In that case, we just ignored the edges, just assumed you were connected to your nearest neighbors and used information based on the XYZ coordinates. And then we went on to the more complicated algorithms, which only assume the edges are there, because if it's the World Wide Web, there's no XYZ coordinates. We talked about two partitioning methods. One was called Kernighan-Lin, and where you iteratively updated a starting guess for a good partition. And the other one was called spectral bisection, where we said, let's build a trampoline out of our graph where we replace each edge by a spring and watch it vibrate, pick the second frequency, second mode of vibration, where half of it's up, half of it's down. The up half is one partition, the down half is the other partition, and there were lots of pretty theorems that said that was a good idea. So the trouble with all those algorithms is that if you apply them to the original very, very large graph, they're kind of expensive. So the next big idea is to apply these ideas in a recursive way. So what we're going to do is take our original graph, replace it by one, let's say half as big. Welcome. Oh dear, okay.
If there's a sign down there, I didn't see it, and I looked.
Okay, well, glad you could make it. There's still a few comfy chairs left. So today the idea is that we're going to take our big graph. It's too big to apply these algorithms directly. Replace it by one that's about half as large. Partition that. Use that as a starting guess for the original one and improve that. Even if we take half the points, it's still too big, so we have to take half of its points and apply that idea recursively, and that's what multi-level is about. So let us now define some notation and write down the algorithm in a simple recursive algorithm, then give the actual techniques that we use for picking half the vertices and solving the simplified problem. So my original graph is going to have nodes and edges, and when I put a C as a subscript, that's going to be the coarse approximation. And so here is a picture of what the algorithm looks like on one page at a high level. So it's called multi-level, and it takes the graph as input and gives you the two partitions as the output. And if the graph is small enough, then you say, well, I'll just run Kernighan-Lin or spectral bisection directly. That's the base case, and I'll return that partition. Otherwise, I will coarsen my graph somehow to get a graph, start with a big one, get one about half as large. That's step 2. And then call my subroutine recursively on that one. So that's the green step 3. So I'm going to call the same subroutine on this half-size problem. It's still so big, I call it on the half-size problem, call it on the half-size problem, until finally it's so small, the first branch of the code gets taken, and I do partition this small problem, and I get that partition, that little jagged line down the middle. So now I begin returning. I now hit the line of code that says that where I've returned from this, I've returned the course. I need to expand it. So that means I need to take this partition of the graph of half the size and make it a partition of the big one. And so this little black line separator turns into this bigger black separator. That's my starting guess. It's not perfect. So what I do then is I optimize it a little bit, and I get the green one instead. So that is the slightly better one. Then I return again. I take that green one. It moves up here. I optimize it a little bit, and I get this better partition, and I keep moving up the chain. And this is called a V cycle because obviously it looks like a V when I've drawn it. And that's terminology that's going to come up later when we talk about multi-grid because, as I said, this multi-level stuff is a big idea. People use it all the time. So that's the basic outline. And all I have to do is tell you how the 3 blue subroutines work, which is how do I coarsen to get a graph that's about half the size? How do I expand it so that if I have a partition of this little guy, I can get a partition of the big guy? And then how do I do the iterative improvement? To start with the starting guess. And I mean, we've seen that already, right? Kernighan-Lin, that sort of thing. Okay, so let me do there are 2 ways to do it depending on whether your iterative improvement routine is Kernighan-Lin or spectral bisection. So let's talk with Kernighan-Lin. So the coarsening and expanding is going to be this idea called maximal matchings from graph theory. And so I'll define that in the next slide. And then the improvement, as I said, we've seen already. So let me define a maximal matching. So a matching of a graph with a bunch of edges E is a subset of the edges so that nobody shares an endpoint. So that every vertex is happily married to exactly one other vertex. And I have a bunch of edges that do that. Okay? And a maximal matching, welcome to the executive conference room. And the maximal matching is a set of edges that I've chosen where I can't add any more, where somebody would be partnered up with more than one other vertex. So how do I compute a maximal matching? And the answer is there's a very, very simple greedy algorithm. Linear, runs in linear time, which is why I can afford to do this. So I'll start by having chosen no edges in my matching. Then I'll just walk through the nodes in any order. I'll look at each node and say, have I visited you yet? No. If not, then I'll mark you as visited, as matched. I'll look to see if you have an edge to somebody else who's also not matched. I'll pick any partner, available partner, and if I find one, I'll just add that edge. And I add that to my list, and I mark your partner as having been matched. And I just sort of walk through all the vertices until I can't add anybody more. So let's run the algorithm on a little graph and just see what happens. So here's my graph. And I'll visit the vertices in numerical order. So I'll start with vertex 1, and I'll say, visited you. Can I find an unvisited partner? Yeah, vertex 2. So I'll grab the edge that I've colored red and add that to my matching. Then I go to vertex 2 and say, oops, I've been there already. Then I go to vertex 3. OK, you haven't been found. Let me look at all your neighbors. Well, 1, that's partnered. 2, that's partnered. Now I'll grab 6. That hasn't been visited yet, so I add the red edge. Then 4. I look at the, 2's been partnered, 3's been partnered, 5 hasn't been, so I grab the edge from 4 to 5. Then I go to 6, been there already, go to 7, grab 9, and 8 is left, lonely at the end, the odd person out. So my red edges are the maximal matching. So very simple. So now, what do I do to coarsen? So let's suppose now that this is my graph, and what I want to do is replace it with a graph of half the size. And it's very simple. I take every one of these red edges and I replace it by a single vertex. So in other words, I just take these two nodes and I merge them together into one node. And so I've just drawn a circle, so these red circles correspond to the nodes in the coarse graph. And what about the edges? I need the edges in the coarse graph. So the edge that connects these two inside one node, that just goes away. But now I look to see, well, there are edges from these two vertices to that vertex. And so that means I have to have an edge from this new supernode, coarse node, to that coarse node. What should the edge weight be? Well, the edge weights here are 1 and 2, so let me just add them up. So I'll give an edge weight 3 from that new vertex to that new vertex. And I just sort of build the new graph. And obviously it's going to have a lot, by design, almost exactly half as many vertices and a lot fewer edges as well. And so this is going to be the guy that I coarsen. And everything I just said there, by drawing an obvious picture, there's the code for it. But I mean, it's just the longhand way of saying what I just said with a picture. So you can read that at your leisure. So now the question is, what do I do when I partition my coarse graph? So now I've got my coarse graph. I call the subroutine recursively, and I decide that's my partition, that green line. So now what I need to do is make a partition on the original graph, and that's pretty obvious how to do it, right? So the vertices that land on this side land on that side of that partition, and the ones up here, they land on that side of that partition. So it's very easy to see how to do that. So that is the recursive Kernighan-Lin partitioner, and that is the basis of most of the, or many of the tools that are actually available. Because this is an important problem. People build many libraries. You can download it. But this is how it works. Now I'll give you pointers to the software later. Yes, question, and there's a microphone.
Jesus. Where's these?
At the bottom.
Well, I'm apparently not smart enough to figure out the microphone, so I'll just ask my question anyways.
Okay. Somebody may come out and help in a moment. We'll see.
Sure. The maximal matching. It seems like there's many maximal matchings you can establish.
You can walk through the nodes in any order, maybe get a different one.
Mm-hmm. So is there any...
That's okay. Because remember, all these are heuristics, because the problem of finding the optimal partitioning is NP hard, and in fact, finding a maximum matching is also hard. And that's not the problem we want. We want the cheap linear time maximal matching, which means you just can't make it any larger.
Okay.
Yes, another question.
So what makes this specific to Kernighan-Lin? Is that...
You're saying, why could I not use spectral bisection for
the bottom of the V and then use this?
So the question is, how do you do the iterative improvement? And so what you'll see for the next way, the way that I do the partitioning makes it much easier to get a starting guess for an eigenvector from the coarse problem and make that a starting guess for the find problem and iteratively improve that. It just follows more naturally from maximal independent sets as opposed to maximal matching. They're very similar graph problems. They're slightly different.
Okay.
Okay. So now let's talk about how you would do spectral bisection recursively. And I'm going to replace maximal matchings with maximal independent sets, a very similar idea. And so that means I need to get an approximate eigenvector from the coarse problem to the fine problem. And there's a well-known linear algebra algorithm called Rayleigh quotient iteration, which iteratively improves eigenvectors that I'll tell you about. So let me define a maximal independent set. So an independent set is a subset of the vertices now, not the edges, so that no two nodes are connected by an edge. It's kind of the opposite of a matching, right? Nobody's connected. And a maximal independent set is a subset of the nodes so that nobody's directly connected to anybody else. You can't add anybody without finding a match. And so again, there's a simple, greedy, linear time algorithm to do this. We'll visit the nodes in any order. And so I'll look at each node and say, are you a neighbor of anybody I've seen before? If not, I'll grab you. So let's see, is this easy to see? Yeah, that's blue. So I'll grab you. I'll put that in my independent set. I'll look at the next node. I can do this in any order. You're a neighbor of somebody I've seen already, so I can't pick you. Then I go to the next one and say, nope, none of your neighbors have been selected, so I'll select you. And you just keep marching through the vertices in whatever order, and you just pick somebody if you haven't picked any of its neighbors yet. So it's very simple. And when I'm done, I've chosen maybe about half the vertices to go into my independent set. It doesn't have to be half. If I have very high out degrees, then I pick one vertex, and all its neighbors are now off limits, and so I may actually pick a much smaller subset than half. It depends on the degree. So now, how do I coarsen? So here's a picture. What I'm going to do is now I've labeled the vertices as being either independent or not. I will walk through all the vertices and say, all right, you're an independent one. I'm going to create a new coarse node to which you belong. I'll call that D1. Then I'll look at the next vertex and I'll say, okay, you're not selected as independent, but you're connected to this other independent guy. I'll throw you into that guy's partition that I just created, D1. Then I'll look at that edge that created you, and I'll just keep that inside D1. It's not going to be part of the edge of the coarse graph. Then I go to the next one. I say, oh, you're independent, so I have to create a new coarse node for you. What other coarse nodes are you connected to? Well, you're connected to him, so my coarse graph will have a new blue edge connecting this coarse node to that coarse node. And I just keep walking through it, kind of doing the obvious decision making at each point. And it runs in linear time. And there's the code for what I just said in English, if you want to read it later. But I mean, hopefully the English description was enough to see that I'm just walking through and making the obvious decisions. So here, what I end up with is I started with 2, 4, 6, 8, 9 vertices, and I end up with 5, about half as many. And it's still a linear graph, so it's an obvious way to approximate a long linear chain with a short one. In general, the graphs will get more complicated. Okay, so now I have to say, how do I extend a partition of my coarse graph? Remember, I'm doing spectral bisection, to a partition of the finer graph. So what that means is I have an eigenvector for the second smallest eigenvalue of the coarse graph. That's, I'm going to say, an approximate eigenvector in some sense for the fine one. And I need to update it. I need to make it a more accurate second eigenvector. And so how do I do this? So I'm going to use the simplest idea possible. I'm just going to do interpolation. So I have a value, a number, an eigenvector component, a real number between 0 and 1 for each coarse vector component. And since each of those points, each of those vertices corresponds to an original vertex, I'll just assign that number to the corresponding original number. Picture on the next slide. So what if you're not a member of the independent set? I threw you out. Well, you're connected to some neighbors. Your neighbors are independent sets. I'll just take their average value. So it's a perfectly natural way to do it. Let me draw a picture for the case of the one-dimensional chain. So here I have 9 vertices connected linearly in a chain. That's the fine mesh. And then the coarse one is I take every other point. So that one, that one, that one, that one, and that one. And so the coarse eigenvector I've drawn here has these values. So it's the dotted blue line. So the eigenvector for the 5 by 5 matrix looks there, 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 and there, those 5 points. I've connected them by dotted lines, and that's just interpolation. So now for the intermediate points, I just average the two nearest neighbors. And so the blue dotted line is my approximate eigenvector for the 9 by 9 problem. And to see if that's a good approximation or not, let me renormalize it, right? So it has 2 norm 1. And then what I get is the purple line, the purple x's, right? That's the normalized one. Let me compare that to the true eigenvector. That's the black line. So no surprise, the black line is the true 9 by 9 eigenvector, and it's pretty well approximated by the interpolated one. So that's going to be my initial guess. But that may not be here I could stop at this point and I'd still get a perfectly good answer, but in general it's only a starting guess and I need to do some iterative improvement. And so the algorithm for doing iterative improvement is called Rayleigh quotient iteration. And I will just describe it very briefly and then show you a picture of how fast it converges. It converges really fast, cubically convergent. So you get triple as many digits at every step, so you don't take very many steps of this algorithm. And so what does the inner loop look like? I'm going to start with an approximate eigenvector, V0, and I'm going to generate a sequence, V1, V2, V3, that keep getting better and better. And at each step, I'm going to take my last eigenvector approximation and get an eigenvalue approximation from it by computing this. It's called a Rayleigh quotient. It's just the matrix times a vector and then dot product with a vector. If that were an eigenvector, this would be exactly equal to an eigenvalue, just by the definition of an eigenvalue. But that's going to be a good approximation. Then I take my matrix, subtract the eigenvalue from the diagonal. That would be exactly singular if I hadn't made a mistake. So when I invert it, that sounds dangerous, but it's okay. That matrix is pointing really strongly in the direction of the eigenvector that I want. So when I solve this linear system, this is a much better eigenvector approximation. And then I just repeat. And this is a classical algorithm, and it triples the number of correct digits at every step. So it's cubically convergent. And so here's a convergence plot just to show you. And I'm showing you the convergence for the eigenvalue in the blue dotted line and for the eigenvector in the black line. And I start with 1 digit. And after one step, I get 3 digits, and then I get 8 digits, and then I run out of precision, right? Because I can't get 24 digits, right? I'm only running in double. So we don't run this algorithm very long. Let me go back to this step here. This is a matrix vector multiply, sparse matrix vector multiply. That's the no free lunch principle, right? That's the problem we're trying to optimize. We have to do it there. This one looks a lot worse, right? This is solving a linear system with that sparse matrix. So we're not going to do that very accurately. I mean, if we're tripling the number of digits, we're not going to bother working at it too hard. So how am I going to solve that sparse linear system? I'm going to use an iterative solver. What's in the inner loop? Sparse matrix vector multiply, right? So it's one of those standard methods. And the one that happens to work very well for this special kind of symmetric matrix is called SimLQ. And it's one of those standard so-called Krylov subspace methods that we'll talk about, if not today, then the next lecture. Conjugate gradient, it's all in that kind of class of problems. Okay. So that is the end of multi-level acceleration. Any questions before I show you some performance data? Yes, and there's a microphone.
Looking at that graph of the averaging the eigenvalues, it looks like you could do a little better if you did something other than linear interpolation. Have people tried that, and is it worth it if the next step converges so fast anyways?
I'm going to guess that it probably doesn't help too much unless you have some problem-specific information that helps you interpolate. So the problem where people have had the most success with using this is in image segmentation. And for some reason, so this algorithm is much slower, we'll see that in a moment, than Kernighan-Lin. But people still like to use it for image segmentation because it captures the properties of the images better than Kernighan-Lin, and they're willing to pay the price for it. And so that would be the literature that I'd have to go look in. Jitendra Malik here was one of the pioneers in this, and look to see what they tried to do. Yes, please.
Can you just go over the difference between the two ways that you walked through each of the nodes and decided I didn't understand how they were different if you compared
independent sets,
yeah,
and maximal matchings. So in one case, all right, let's go through here. So in this case, I walk through the vertices, any order is fine, and I grab the first other vertex that had not already been visited. right? And so that becomes my partner. And I mark them both as having been visited, and then they're off limits, and I just keep grabbing unvisited vertices in the first partner. And so here what I do is I look for an unvisited vertex, and I look at the next guy, and if I'm connected to him, I don't want him. So I say, I can't pick you because you're a neighbor of somebody who's already in my independent set. So instead of matching, I'm looking for independence. Then the next guy is not connected to somebody in the independent set, so I'm willing to take him. So he's in my independent set. The next guy is connected to somebody I've seen before, so I skip him, then go on to the next one. So it's sort of a little bit of the opposite.
So in the first one,
Question?
In the first one, the things that we try swapping in Kernighan-Lin are the connected pairs. Is that why?
So in Kernighan-Lin, we go back to the original graph, and we take vertices on opposite sides of the partition. We ask, is it worth swapping it?
Okay.
Yeah. So so you're asking perhaps, could I use maximal matching with, could I use independent sets with Kernighan-Lin as opposed to doing it the other way?
Yeah.
I think that I can't think of, let's see, a big obstacle right now, but in the past people have generally used the maximal matchings with Kernighan-Lin. So there's probably several ways to glue this stuff together. Okay, so now let me show you some admittedly old data comparing the performance of these. But actually, let me start by telling you about available implementations, because this is, widely used stuff. So people have worked very hard. There's some teams who get together and have built these things. So you should not build it yourself, unless you want to do research in the area. So Metis was one of the first ones, which does multi-level Kernighan-Lin. That's a sequential implementation. ParMetis is a parallel version of that. Scotch is despite the name, built in France, and that one may be actually getting a little bit more maintenance right now. It has had more recent releases than ParMetis has, and those are both multi-level Kernighan-Lin. For spectral bisection, Chaco is the one that I might point you to. That's at Sandia National Labs. And it's also possible to hybridize these, as you had mentioned. Now, there's a recent package developed by some folks at the Department of Energy, which is kind of a front end to all of these different things. It's called Zoltan. They like names there. I can't remember the actual historical reference for that one. And it's part of the Trilinos package. And so they give you a sort of a front end to all of these different packages. And if you're willing to, use their kind of way of formulating your problem, you can access any of these and try one and try the other. And there's a good web page which has sort of a description and comparison of all these methods here at Bruce Hendrickson's web page. So let me give you some comparison data on a big set of graphs, a big set of not so big graphs. And so what are the metrics of success? One of them is how long it takes, obviously. Another one is how many edges do they cut at the end, the fewer the better. And then there may be other application-dependent metrics. So, for example, we'll see spectral bisection is much slower, but people in image segmentation like it. So that's a separate kind of metric. There's no one best method, which is why all these packages exist. But we'll see that Kernighan-Lin is much faster, multi-level Kernighan-Lin than the multi-level spectral. And there's the paper by Jitendra Malik, which explains why that's the case. Okay, so here's a table of lots of data. Let me try to explain it. For each row, there's a different graph, and here's where the graphs come from. Some of them are 3D finite element meshes, some are 2D, some come from circuit simulation, or they're actual circuits, like a 32-bit adder, linear programming, Navier-Stokes, and all of these are publicly available. They're web pages where people collect sparse matrices, which are graphs, and so you can apply this to and do experiments. Here are the sizes of the graphs in terms of the number of nodes and the number of edges, and you can see that some of these are pretty tiny by today's standards. And so for each of these, you can say, how do we ask, are you doing as well as we expect? What we can do is take each of these graphs, take the number of nodes, and pretend it's a 2D mesh, and say, if I partitioned you in the perfect way I understand how to partition 2D meshes, it's about square root of n. How many edges would I have to cut? if I wanted to cut you 64 ways, right? So an 8 by 8 grid, and that turns into about 17 n to the 1/2. And I could ask the same question if it were a three-dimensional mesh. How many edges would I expect to cut with all the planes? And it grows like n to the 2/3. And so I can have the expected number of cuts for a 2D mesh or a 3D mesh. Just for get some sense of what to expect, here's the number of edges actually cut. And so in this first 3D mesh, 88,000 edges versus an expected 31, well, maybe that's okay. It's certainly, we expect to have to cut more edges in the three-dimensional mesh because there's more connectivity. Here's a two-dimensional one, and indeed the two-dimensional number of edges cut is closer to the numbers I'd expect. The story isn't so clean for all the other ones, but it is one way of sort of guiding your expectations. So anyway, so this is, as I said, rather old data, but there's more new data on the web pages that I gave you pointers to. Here's the second question, which is how long it takes. It's the same set of sparse graphs. And here's time in seconds, spectral bisection versus Kernighan-Lin, and Kernighan-Lin wins by an order of magnitude, right? So if you want to minimize edge cuts and time, then this one wins. This is what's in most of those packages like Parmetis and Scotch. But if you have some particular application that needs the special properties of spectral bisection, then you're willing to pay that. Okay. So that's the end of graph partitioning. But there is another topic. But are there any questions about graph partitioning before I go on to hypergraph partitioning? So the reason to talk about hypergraphs is that a graph is not necessarily the best way to describe the communication in sparse matrix vector multiply, or indeed in any of these kind of things. It's a perfectly fine approximation. It's a great approximation if you have a symmetric matrix, but it's not a very good approximation if it's not symmetric. In other words, if the communication does not go in both directions automatically along each edge. So let me just show you what a hypergraph representation is of this very small, slightly non-symmetric matrix. So I'm going to have so I'm going to represent it here initially as what I call a bipartite graph. So I have one vertex for every row, 1 through 4, one vertex for every column, and one edge for every non-zero. So this is kind of completely isomorphic to that graph, right? I've lost no information. And it also captures the fact that column 3 has 3 non-zeros in it, connected to rows 1, row 2, and row 3. Now, what is a hypergraph representation? The hypergraph is very close to this. What I'm going to do is say for each column, I'm going to have not an edge, but a net. And the net is going to have, say, what are all the rows I'm connected to? So, for example, there's one net for column 3, and that net is like an edge, but it doesn't have 2 endpoints, it has 3 endpoints, because column 3 is connected to rows 1, 2, and 3. So 1, 2, and 3. And so this net here, which I'm calling column 3, is sort of this hypergraph net kind of edge with 3 endpoints. So that's what you represent a hypergraph as. So let's see why this hypergraph does a better job of counting communication than a regular graph partition. So let's suppose that I want to partition my problem this way. I have two processors. Processor 1 gets the first 2 rows, processor 2 gets the second 2, and I want to do sparse matrix vector multiply. And so I want to count how much I have to communicate between processor 1 and processor 2. And so let me count the number of edges that go from one to the other. So how many red edges go from processor 1 to processor 2? And the answer is 1, 2, 3, 4. Right? So it's telling me that I have 4 edge cuts. But now let me do it differently with nets. So here is one net, which is the one that, so let me be more specific here. So this purple stuff, these are all the columns that the first row needs. I only need information about columns 1, 2, and 3. I don't need to know column 4. So the purple oval circles all of the values of x that I need to do the matrix vector multiply for the first 2 rows. And the red oval circles everything I need to know to do the matrix vector multiply for the last 2 rows. I only need to know the data in that column, and that column, because those are all zeros. And that is what's captured by these nets. So what do I need to communicate? C2, column 2, that's the value of x2. That's owned by the first processor. It needs to be sent to the second processor because I need it for both those entries. But I only need to send it once. right? I need to send the value of x2, it'll be used twice. That's captured by the idea that there's one net. And similarly, right, I only need to send one value, this value, x3, I have to send it once to the first processor and it'll be used twice. So that means that the volume of communication is 2. But when I when I modeled this as a graph, on the last slide it was 4, but here's another way to look at it, and it's 3. Either way it's wrong. It should be 2. So processor 1 is going to have a vertex 1, and it's going to own nodes 1 and 2. Processor 2 is going to own nodes 3 and 4. Where are the edges? I just sort of think of this now as a symmetric matrix. And so 1 is connected to 3, 2 is connected to 3 and 4, and 4 is connected to 2. So there are going to be 3 edges crossing there. But I only really have to send 2 pieces of information. And so the point is that this hypergraph does a more accurate job. It doesn't throw away any information of saying how much information has to pass back and forth. So let us see what impact. This is such a tiny problem. It's maybe not so interesting, but it sort of explains why it doesn't count right. So now let me go to a more interesting problem, a two-dimensional mesh, and compare the answers I get from graph partitioning it versus hypergraph partitioning it. Okay, so here I have a two-dimensional mesh, and I don't know why that blue dot doesn't show up. Thank you, PowerPoint. And so what is the traditional? So it's a 64. It's a 16 by 16 two-dimensional grid. Everybody's connected to its 4 nearest neighbors. I want to spread it over 4 processors, and here's the partition that we've used all along. And so what do I need to communicate? Everything has to go left, right across that boundary, up, down across that boundary. The answer is 64. What if I do hypergraph partitioning? What's optimal? This is what it looks like. This is the right way to partition that. And what is the intuition here? This guy on the boundary, he has 2 neighbors, but he only has to send 1 piece of information because that pink dot and that pink dot only need the same number from that guy. That guy also only has to send 2 pieces of information. That guy also has to send only 2 pieces of information. So the total communication is the length, the number of vertices along that diagonal. And if you add it all up, it's only 58 instead of 64. This problem is still too small, but still, this is, if you really want to be optimal, the right partition. Yes?
I just want to make sure I understand the intuition behind this. The intuition behind the hypergraph model is that moving data between partitions, you can sort of do away with the idea of duplicate transmission, and then moving the data within a partition is assumed to be essentially free.
That's right.
Okay.
That's right. So that part is shared between these 2 models. If it's all local, you don't pay for it. I only care about how much has to pass from one processor to another, one color to another. And if I count correctly, I will notice that this is less because that one guy, even though he has 2 neighbors, there's 2 edges crossing, it's the same piece of information. And that's captured by a net. So how does this work? How does this scale up? If I do a general large partition, how much do I save in the asymptotic case? So here's what the partition looks like kind of in general if you try to scale it up. And if you ask, how much can I save versus the obvious 2D horizontal vertical partitioning for an n by n mesh on a p by p processor grid, the usual partitioning costs me 4 NP. That goes down to 3 NP. All right, so it's a 25% savings, which was a surprise when people discovered it. It's not necessarily something that you want to do in practice for this particular graph, because you can imagine that generating the code, for all of these partitions on any particular processor and figuring out who you have to communicate with your neighbors is rather more complicated than just north, south, east, west. But nonetheless, this is the right answer, and as far as we know, it's asymptotically optimal. So this is the theory. What about the practice? Because people have built not just graph partitioners, they have built hypergraph partitioners. So let us now take that software, which is called PATO, and see what happens when we apply it and see how well it does. So here I've taken that same mesh with north, south, east, west connections, and I've asked Metis to partition it, and I've asked the hypergraph partitioner to partition it, and to see how well it does. So I've color-coded it by how it works. And neither one does what the theory suggests, because they don't have a special case for 2D meshes, right? They're applying the general theory and multi-level and all of that. And so nonetheless, Metis does a reasonable job of kind of approximately coming up with a 4x4 mesh. And this is sort of diagonal. And it does actually, reduce the communication volume. If you look at, if you look at the critical path, the maximum processor, this guy is sending 69, and this guy is sending 59. And so, it's not the 25% we saw before, but nonetheless, this is kind of working. So let me give you another example where the benefit is even more dramatic. This matrix, if you were to write it down, is still symmetric, right? Because everybody's connected to the nearest neighbors. The examples where hypergraphs are much better, and it was my original one, is where the matrix is non-symmetric. So let's try the most non-symmetric matrix you can think of, which is triangular, right? That's pretty non-symmetric. And see what happens when I apply graph partitioning versus hypergraph to a triangular matrix. And so the thing to notice is that if I take a triangular matrix and ask, what does graph partitioning do? Graph partitioning has an edge whether a sub ij is non-zero or a sub ji. So in other words, you get the same graph whether you use a or a plus a transpose. And if your matrix is fully triangular, then a plus a transpose is dense, right? You don't have very much information at all. So let's just try it and see. I'm going to take a dense upper triangular matrix and apply Metis, and I'll apply Pato. And so here and divide it into just two pieces. And so here are the partitions that you get. And now the communication has dropped rather more dramatically from 254 to 181. But even better, the load imbalance is a whole heck of a lot better. It's 0.1%. Basically, it's perfectly balanced versus 6%. So these are all kind of toy examples, but they give you the sense of when you might want to use hypergraph partitioning as opposed to graph partitioning. And we'll have one more example by the end of next lecture where we've been using it too. Yes?
Just for two processors? So how does it scale?
A bisection. Yeah, right. And to two processors, red and green.
And does this work as well for a triangular matrix on n processors? Or p
well, yeah. I mean, so I believe the... I haven't looked at Pato for a while, but I believe the same principle is repeated bisection. Did you have a question?
So I'm having a little mental trouble mapping my pictures of graphs into pictures of the upper triangular matrix. And I'm trying to just wondering, like, what example graphs might have this property to start with?
So upper triangular matrices happen every time you do Gaussian elimination. Mm-hmm. You get an L times U. They're both triangular.
Right.
And we need to do lots of different operations with those triangular matrices, like triangular solve and multiplication by them, depending on the algorithm. So they're very common.
Do they arise in sort of naturally occurring graphs as well, or sort of do you come about it from the linear algebra side?
So the other place that they come up in is if you take a general graph and do topological sorting and reorder the vertices, in the topological sorted order, which tries to make it as triangular as possible.
Okay.
So that is topological sorting means you have a directed graph, you have arrows, and what you try to do is reorder the vertices so all the arrows point forward to the extent possible. And in this particular, in this case, all the arrows point from lower numbered vertices to higher numbered vertices. But you might end up with little blocks too. So, okay, so let me now summarize this part of the lecture, which is graphs versus hypergraphs. Which one would you choose when? So if the matrix is really non-symmetric, then the graph partitioning model loses all that information because it always is as though it were working on A plus A transpose. And so you could get a suboptimal partitioning. And even when the matrix is symmetric, 2D meshes connected to all your nearest neighbors, it's not optimal. I mean, it was within a constant factor, but it's not optimal. Now, the trouble is, though, that all the hypergraph partitioners are significantly more expensive than the graph partitioners. So you have to have a special problem to be willing to do this, but depending on your problem, and we'll see one next time, it may pay off to be willing to do this. And hypergraph partitioners are available. Metis, there's an H-Metis version. Pato, and there's interfaces to all these in that bigger package Zoltan that I told you about again. And if you want to hear another amusing lecture on why hypergraphs are better than graphs, you can read this lecture on fictions, falsehoods, and fallacies on Bruce's webpage. So that's all I wanted to say about graph partitioning. And now I want to go on to one application of it and illustrate auto-tuning for sparse matrix vector multiply. But are there any questions about this before I go on? Okay. Okay, so now I'm going to be talking about one particular sparse matrix vector operation, which is sparse matrix vector multiply, and all the different things you have to do to make it go fast, of which partitioning is just one, but actually a lot of this talk is going to be about the sequential optimization. So it's a homework one in some sense revisited, but with lots and lots of other more complicated transformations for this particular problem. So I'm going to give you some motivating slides for automatic performance tuning beyond what we've already seen in homework one. And I'll tell you about some results for sparse matrix kernels and some very large speedups that we get. We've released a package that does this, just as you heard about Atlas for auto-tuning matrix multiply. There's a package we released called OSCI for optimized sparse kernel interface. That was done a while ago just for doing sequential optimizations. And last year we released and just did a re-release of POSCI, which is the parallel version. And of course, OSCI is coincidentally the name of the Cal Bear mascot. Complete coincidence, of course. And then I will talk about tuning higher level algorithms. That's the fun part. Not just a single. The thing about a single sparse matrix vector multiply, it's going to be memory bound because you're doing 2 floating point operations per non-zero entry. And that's going to give you certain limits that you can't get past. Unless you look higher up in the algorithm, for example, a linear equation solver, and say, well, I'm doing lots of sparse matrix vector multiplies. Can I reorganize the algorithm to take advantage of that and do parts of those multiple sparse matrix vector multiplies at the same time and reuse the data? And then I can get much larger speedups. But that requires reorganizing algorithms higher up the mathematical stack. We'll do that next time. And there's plenty of future work in class projects, and we have weekly group meetings in this to which you're welcome to attend, and they're free lunches. Okay. So as you gathered from homework one, writing high-performance code is hard, and it's not getting easier as the architectures get more complicated. Ideally, we'd just like to write it all in our favorite high-level language like MATLAB or Python, PETC perhaps, and just get a high fraction of peak. And so let us talk about how to automate some of that. And the difference between this problem and the problem you did in homework one is that you don't have enough information to do it offline. You can't just spend a week or a month optimizing dense matrix multiply and you're done, no matter what your dense matrix is, because you don't know until runtime when the user hands you his or her sparse matrix what the pattern is and how to optimize it. So that makes the problem quite different. And so these are some examples that we've mentioned before for the dense BLAS, for fast Fourier transforms, for signal processing in general. This is now, I believe, become a startup because it's such a popular idea. People have been also trying to auto-tune communication collectives. How do you design the reduction trees and the broadcast trees? And there's a whole bunch of work where people are trying to embed this into compilers so that you can write your code in a high-level language and it will automatically do the auto-tuning. And of course, we're doing that here in the CJITS project as well. And there's more literature than I decided to fill in the slide here, but you can ask about it later. So what all of these guys have in common, as I said, is that you can do it in principle offline. You know that, if you know the dimensions of your matrix and the number of processors, say, that's all you need to know in order to pick the right algorithm. You can spend a long time trying to optimize it. And so let me just show you an example of what that tuning space is, which is why it takes a long time. And we're going to do some of this for sparse matrices too. So in other words, offline you can afford to spend as much time as you want. And we're going to try to divide the work in sparse matrix tuning into the offline part where we can take the time and the online part. So let me just show you this picture about tuning register sizes to show you why we want to automate it. And we'll see another version of this in a moment. So I want to pick a tile size for doing my sparse matrix multiply. And so I'm going to try a whole bunch of different possibilities. It's going to be an N0 by M0 block. And both of those values are going to run from 1 up to 16. This ancient processor has 16 registers, so it's only worth picking a tile size that fits in the register. So N0 times M0 has to be at most 16. So that means I'm only interested in these blocks below this hyperbola of NM equals 16. And each one is color-coded by how long it takes. And the winner, of course, is this little brown dot up here, which is a 2x3 block running at 600 megaflops. And that is the needle in the haystack that you can do by hand if you really want to, and some people used to do it that way, but it's obviously much more effective to write a computer program that tries it all, generates the SSE instructions, whatever else you have to do, and discovers that automatically. Now, the other thing we may discover is that depending on your problem size, there is no one best algorithm. So suppose you discover that one particular algorithm with one particular block size choice is good for problems in this size, and then for problems in a different size, you have to do it differently. So here's an example where we did that experiment. And so this is for matrix multiplication where there are 3 different algorithms to choose from, a blue one, a red one, and a green one. And we tried them all on problems of an m by k times a k by n matrix multiplication, so rectangular. That's why it came out this way. And so m and n were equal and k was different. And what I've done here is I've put a little dot every time we did an experiment. We tried each of the 3 algorithms, and the dot says who won. So the blue algorithm tended to win out here most of the time. The green one won occasionally. The red algorithm won there, and then there was this sort of fuzzy place here. So the question is, how do you quickly, so this is information you collect offline. What do you do at runtime to decide quickly which one of the 3 algorithms to use? And one of the standard techniques, just to illustrate, is a technique from machine learning called support vector machines. And I'm not going to, you can learn about support vector machines in the machine learning class, but what you can do is build a predictor that very quickly tries to draw curved boundaries between these regions, which do a pretty good job of distinguishing between one side or the other. So let me now show you the decision made by the support vector machine versus the truth, and I'll just toggle between them, and you can see that they don't differ very much. It did a pretty good job of picking the right one. So near the boundary, it might change its mind. But so, for example, right there, the green one won in those 2 points. In truth, the support vector machine chose the blue algorithm instead. But near the boundary, all these algorithms are running at about the same speed, so you might only lose a few % by making the wrong decision anyway. So these are some of the tools that you need to grab from other fields, machine learning, in order to do the quick choice of algorithm at runtime. And here's some literature where it describes the use of these tools and how we use machine learning to figure this out. But it's an ongoing problem, and people are doing work in this. So that is, in some sense, the easy part of the problem, because you can do it all offline. You can use all these fancy tools. But we can't do that for sparse matrices, because it's the actual choice of the algorithm is going to depend on when the user hands us the matrix at runtime, where the non-zeros are will actually greatly affect the choice of algorithm. And so let me now show you some examples of why that's the case by showing you some sample matrices. So here's a spy plot, for example, of something from a collaborator at Stanford at SLAC, at the Linear Accelerator Laboratory. This came up in designing a new accelerator cavity design problem. And this isn't a terribly large matrix. It's a to be able to make a spy plot, you can see we took a little submatrix of their much bigger matrix. Here's one that came out of some sort of economic modeling. They tend to get long, skinny matrices for doing linear programming. And this, in fact, this is just the first 20,000 columns of a 4,000 by 1 million matrix. And here's a matrix that billions of people use every day. So what do you think it is? The web, obviously, yes, right. So, and if you're not paying attention, you're probably using it right now because you're looking something up, right? So it's a little tiny piece of a matrix, of course. This is from on some Stanford database where they collected these things. And again, the question is, how do I do a sparse matrix vector multiply quickly? And indeed, the original PageRank algorithm, which is how Google got started, did lots of sparse matrix vector multiplies with precisely this matrix in order to do PageRank to figure out how to order things. So let's now look at the different algorithms for doing sparse matrix vector multiply and what are our tuning opportunities. Hello. Okay, there we go. So let me remind you of the most basic, simple algorithm and the data structure that goes along with it. So here's my sparse matrix, and clearly I don't want to either compute the zeros or store the zeros. So compressed sparse row format will simply take each row of the matrix and store it as a contiguous vector. So those 4 red non-zeros in row 1 all get packed together, followed by row 2. I need to remember where they were located, so I have another array of all of their column indices. indexed the same way. And then I have to know where each row begins and ends, so I have a third array of pointers, which points to the beginning of the first row, the second row, the third row, and then an end pointer at the end. And so how do I take that simple data structure and do sparse matrix vector multiply? Let me just write down the two nested loops. They're pretty natural. So for each row, for each entry of the vector y, I need to compute the dot product of the ith row of A with x. So I will loop from the beginning of the row to the end of the row, and the pointer array tells me how to do that, from the beginning to the beginning of the next one, minus 1. And so I get the value in the matrix entry, and I multiply it by the corresponding entry of x. But how do I find the corresponding entry of x? I need to do indirection. I need to go find out what is the subscript of that entry, go to some other faraway place in memory to get that entry of x, bring it in, and then do the dot product. And so that means that I have at most 2 flops per non-zero entry of the matrix, so that it's going to limit my computational intensity. But in addition, I have this indirect addressing, which is a pain. So I'd like to eliminate that as much as possible. So let me do an example and see what tuning looks like. So let me take this particular finite element matrix from a NASA structural analysis problem. These are all available online. You can go grab them and do your experiments. And I want to ask, how do I do sparse matrix vector multiply fast? So let me zoom in the SPI plot and see if I see any patterns. So let me zoom into the top corner. And lo and behold, because it's a finite element matrix, it consists of a lot of little dense 8x8 subblocks. And so an obvious optimization would be, let me not have 64 column indices for all the non-zeros in there. All I need to do is store where is the upper corner located. And then I can change my algorithm to figure out where everything else is. And so I can reduce the number of indices I have to store by a factor of 64. That seems like a good idea if I take advantage of that little dense substructure. So let me now do an experiment where I try that. And so what I'm going to do is store my matrix not in 1 by 1 blocks. I'm going to store it in R by C blocks. So in that last picture, R and C were natural choices of 8 by 8. And so the storage can drop up to a factor of 2, right? I still have to store all the non-zero entries. What I can reduce in the memory traffic is all of those 32-bit or 64-bit integers that I store, and maybe so I can get a factor of 2. So given my sparse matrix, for that one it seemed pretty obvious. I wanted to pick R and C were both equal to 8. But if I have a more general sparse matrix, then I have to pick that more carefully. So let's do an experiment. Let me try that matrix and see how much faster it goes. But let me, while I have the data, let me not just do R and C equals 8, because if I go look at this, I could also break this little block up into 4 4x4 matrices, or 2 8x2 matrices, or all these other possibilities, right? Because 8 has a lot of factors. In fact, I can do 16 different experiments, all the way from 1 by 1 up to 8 by 8. So let me just try all those experiments and see what happens. And so here's what happened. So this is the column block size 1, 2, 4, 8. There's the row block size R 1, 2, 4, 8, and it's color coded by who went fastest. And 2 by 4 1. It was 4 times faster. It was also a good idea to do 8 by 8, but that only went 1.5 times faster. And so why is this? Well, it's some complicated, function of how prefetching is done in the SSE instruction set and how the compiler generates code. And the point is, I have better things to think about. I would rather just have the machine figure this out automatically by trying all. I mean, depending on where you want to do research, you may ask yourself, why is it that 4 by 2 won, and do hardware design and compiler design. That's a perfectly good thing to do. But for most users, they just want to know the answer. And so that's what auto-tuning will give you. And yeah, so there's the optimal. It's 4 by 2. So now let me expand this experiment and say, let me take a matrix with really big blocks in it. In fact, let me take a dense matrix, it has blocks of any size I want, and try all possible block sizes to see which ones win. So I'm going to try all possible block sizes from 1 by 1 through 12 by 12, just to see what happens and do that experiment on this particular platform, which is an old platform. And so here is the data that says how speed depends on the block size. And again, 4 by 2 was the winner. It went 4 times faster. But bigger wasn't necessarily better on this particular platform. This one won because of all of the intricacies of how code got generated. Now, this is the data that I can collect offline. This is a kind of the stuff that you did by hand in optimizing in homework 1 for the BLAs, this is the data that we collect offline to optimize sparse matrix multiply. We only have to collect this once. And then when we get our sparse matrix, and maybe it has 3 by 3 blocks in it instead of 4 by 2, then we will look at this and say, how can I decompose my problem into the block sizes? And actually 3 by 3 is pretty bad. It slows you down. So this is one particular platform. Let me now just show you what it looks like on other platforms, just to show you that it's very architecture and machine dependent. So let me do the experiment going back to the matrix with just 8 by 8 blocks. So here are all those same experiments in IBM Power 3, and IBM Power 4, and Itanium 1, and Itanium 2. That's the problem we just looked at. And in none of these cases does 8 by 8 win. And the winner is different in every last case. So even though the architecture may change from one, change you might think slightly in going from an IBM Power 3 to an IBM Power 4, the decisions you make differ dramatically. So you really have to do this all over again. And if I now do a bit of eye candy, what about the 12 by 12 case? Here are the same 4 platforms, Power 3, Power 4, Itanium 1, Itanium 2. Try all possible block sizes on dense matrices, and you can see there is not much of a pattern here. It's very much random stuff that you just have to search through. And just because it looks cool, here's one more picture. Okay, so this is a Pentium 3, and this is a Pentium 3M. Those are really close together, except this is the low power version. And I don't know, it's actually easier to choose performance, high performance ones on this one for some reason. Okay. So that tells us that choosing these R's and C's is going to be a challenge. Yes?
The numbers, or it says like 11%, 5%, stuff like that?
On the machine that you get.
Okay.
So, and indeed, none of these are very large. They're all memory bound, somewhat dramatically, which is why we have to have later optimizations where we don't just optimize one sparse matrix vector multiply, we optimize something higher level. So let me now do another example of the tuning challenge and why choosing R and C is hard. So this is a matrix that comes from a fluid flow problem, and again, it's available on a database. Let me do the same trick. Let me zoom into the top corner and see what it looks like. And so now there is no obvious single block size that kind of leaps out at you, but maybe the best we can do is 3 by 3. I mean, really, that's probably the best we're going to do. And if I look at this now, there are a lot of dense 3 by 3 blocks there. There's one, and there's one, and there's one. But there's also a lot of blocks which only partially fill in. So suppose I insisted on using 3 by 3 blocks here, then what would I have to do? Well, I'd have to fill in explicit zeros in those locations if I were going to use that data structure. And so in particular, let me just draw little red dots. At everywhere, I'd have to fill in an explicit 0. So if I were to use this data structure, I would actually store half again as many entries as I had before, a lot of useless zeros. And I'd have to do 50% more arithmetic, right? I'd have to read in those zeros, multiply by them, add them, and it seems like this is probably not going to win. Actually, it's 1.5 times faster to do it this way. And that's because the actual megaflop rate is 1.5 squared times faster. The whole thing is running 2.25 times faster than the original code. But since I'm doing 1.5 times too much work, I only see a speed up of 1.5. And why is that again? Again, it's this complicated, machine-dependent answer, but 3 by 3 is the right thing to do. So now, given this bit of complexity, how do we actually decide at runtime to quickly decide that 3 by 3 is best? Okay. So here is how we do automatic runtime register block size selection. So offline, I compute those 12 by 12, color charts, which say if I had dense blocks of size R by C from 1 by 1 through 12 by 12, how fast would they run? And I collect that once. Now at runtime, what do? I finally get my matrix, and I have to ask, how much would it fill in if I chose to break it up into R by C blocks? How many extra entries would I get? In that first matrix with dense 8 by 8 blocks, the answer fill of 8, 8 would have been 1. In other words, you don't get any extra ones. For the matrix I just showed you, this guy, the fill would have been 1.5 because I have 1.5 times as much. That's the ratio of extra work that I have to do. So how do I estimate the amount of time it takes to actually run the code? Well, the time is going to be the amount of work divided by the speed. And the amount of work is going to vary depending on how many extra non-zeros I had. So that's the numerator. And the denominator is the actual speed in that 12 by 12 color plot. So what I do then is I want to choose R and C to minimize this estimated time. So I pick 144 ratios and I pick the minimum one. Now, I can't afford to compute the fill of RC for 144 combinations. That would just take forever copying the matrix in and out. It would just be overwhelming. So instead what we do is that we are going to do statistical sampling of the matrix and only look at a subset of it, ask what the fill is for that, and hope for the best. And we'll see it works very well. So the idea is we're going to sample the matrix. There's going to be some fraction of the matrix, a number s between 0 and 1. And we're going to only take that part of the matrix and try all the different R by C's and compute the fill. And so the cost is going to be proportional to the number of non-zeros times s. And what we're going to do is control the cost by controlling s. The user can give us hints as to how much they're willing to spend to do this particular problem. And there's various sort of statistical techniques that we can use to see if we did a good job. So we could start with a small s, a very, very small s, and we'll get some numbers. Then we could increase s a little bit, and if our answers don't change, we'll declare victory and say they're good enough approximations. And so how much does all this cost by the time you're done, even if you do all these statistical optimizations? Well, it turns out that this heuristic is going to be cost from anywhere from 1 to 11 sparse matrix vector multiplies of the original unoptimized code. So if you're going to do hundreds of sparse matrix vector multiplies, which fortunately many users do, you're willing to spend 1 to 10 to make the later ones go faster. But if you only want to do one, don't bother, right? Because this is going to overwhelm it. But that's only part of the cost. It turns out that it costs even more to actually copy your input, the user's input matrix, from the original unoptimized format to the new optimized format. Just all that copying and moving stuff around can cost anywhere from 5 to 40 sparse matrix vector multiplies. And so, again, you have to be willing to do hundreds or however large numbers of these ones in order for this to pay off. But in many applications, people do. Or in fact, you may use the same sparse matrix today as you did yesterday because you're doing a science problem that takes a long time. You can just use yesterday's information and save a lot of this time. So let's show you the data of how well all this does. And so here is going to be the results of doing these optimizations on about 40 different test matrices. So the horizontal axis is about 40 different matrices. Again, they're all available. And the vertical axis is performance in megaflops. And there are going to be a bunch of different categories. D is a dense matrix, and so we always ask ourselves, how well can we do compared to a dense matrix? That's sort of an upper limit. The next bunch of matrices are finite element matrices, where there's a single block size, like 8 by 8 or 6 by 6. The next bunch of matrices are finite element matrices again, but now they have multiple block sizes because that's a common feature in finite element problem. You have two different materials, different block sizes. Then a bunch of other ones that are hard to categorize. And then there are a few long, skinny LP, linear programming problems that come out of, I think, economic modeling. And so you can see that the reference code, the CSR code, the unoptimized, with 1 by 1 blocks is hanging out at around 300 megaflops and occasionally dropping a lot lower. And if you choose the best out of all 12 squared, 144 possibilities, you end up with the blue performance dots. And so you can see the dense does best, not surprising. And the single block size finite element does next best. And then mixed finite element does better. And then down here, there's some improvement. But you can see, and that's not bad. That's like a factor of 2, but it's still much lower than that. So that's if we do exhaustive search, try all 144 possibilities. What about our heuristic and the little green squares of the heuristics? And so you can see that most of the time the little green squares are dead on the optimal. You get the same answer from this cheap search, and there are a few cases where they miss by a little bit. But the heuristic does a pretty good job. So the other metric of success is how do we do compared to dense matrix vector multiply, right? These are all sparse matrix vector multiplies. I tried a dense matrix. Suppose I just took the BLAS 2, and I knew it was a dense matrix, and I made that run as fast as possible. How fast does that go? I mean, I'm expecting that to be memory bound too. There's dense matrix vector multiply. So it's not going a heck of a lot faster. So that really is an upper bound on speed, right? There are no indices, nothing there. So that's the fraction of real machine peak that we're getting. Okay. So now let me try to explain why this curve goes from up here to down there, right? So what properties of these matrices are limiting us in how well we can do? And in particular, is there some sort of upper bound that tells me I'm kind of doomed down here compared to up there? So I'm going to build a very simple performance model that tries to predict this behavior that we see. Question?
Does this take into account the extra flops you're performing because of
So we are counting flops fairly. So flops on 0 don't count. Yes. So let me tell you what this very simple performance model is going to do. It's going to look at all the different levels of the memory hierarchy. So this is all sequential code. So I'm just worried about L1 and L2 and DRAM kind of stuff. So the flops, the total number of flops will be twice the number of non-zeros, so I won't count the extra 0 entries. And to get a lower bound on time, I'm going to make two assumptions. The first one is that I'm only going to count memory ops and not conflicts. So how am I going to get an upper bound? I'm going to run a benchmark called the stream benchmark. And that is one of those benchmarks that people have that simply accesses consecutive locations in memory, brings them into cache, and then throws them away. So it sort of just says, how fast does your memory run? That's going to be my upper bound on how fast things go. I can't expect to stream in my sparse matrix any faster than this benchmark. And the next thing I'm going to do is I'm going to assume the cache behaves perfectly. That whenever I read in an entry of A, an entry of X, an entry of Y, they never conflict with one another. So neither one evicts the other because they get in the way. So I'm going to assume that the cache has sort of perfect behavior in that sense. And so now, given all that information, how do I write down a lower bound on the amount of time it takes? I'm just going to count the number of hits at each level in the memory hierarchy. So I'm going to count the number of cache levels from 1 to k, so L1, L2, up to Lk. I'll count the number of times the data that I want actually hits in that level, and I'll multiply it by the latency, where I've gotten these latency numbers from the benchmarks. And then finally, there's a bunch of stuff that only hits in memory. I have to go there, and I'll count, and that's the memory latency term from the stream benchmark. So that's going to be a lower bound on how long it takes, and I'll ask myself how close I can get. Now, I'm also going to ask myself, I'm also going to use hardware performance counters. I'm also going to modify this model slightly and say, well, how many times did I actually hit in each level of memory? This is going to be by paper and pencil. I'm also going to do it by actually measuring stuff using the hardware, because the hardware counts how many ones I have. What does the hardware count? It counts misses, not hits. And so all I have to do is a little algebraic translation here, and I can count the number of misses at each layer, and I get the same formula, but this is what the hardware performance counters give me. Okay, so now let me ask myself, how well does this correspond to actual data? And so let me now, before I do timing, let me just do something more discrete. Let me count L2 misses and ask how well do my bounds compare to the actual number of L2 misses, because I can measure that. And so these are the same 40-some matrices that I had before. The vertical axis is the misses per unblocked non-zero, so the number of L2 misses on the Titanium. The green are the actual, and this dotted line is the lower bound. And that assumes that every time I hit the source vector, it stays in cache and is always there when I need it. So that's sort of, I can't do better than that, that the source vector, the X vector, is always there when I need it. And the upper bound, that's kind of the worst case. That assumes that every time I need an X sub I got to go to memory. So, and clearly the lower bound, assuming that X is always there, is a great approximation. The cache is behaving the way I would want it to, except for these nasty LP matrices, which are very long and skinny, and X is very long, and so there's a bit of a gap between the least number of times I can hit X and the actual number of times I hit X. Okay, so let me use this lower bound now and say this sort of justifies it, the formula on the previous slide, and plug that in and actually predict the performance for all those 40 different matrices. So this is the data that we had before for my 40 matrices. There's the actual performance. And here is the upper bound on the performance that I would get by just counting memory traffic. So that's the upper bound using my lower bound on memory traffic. And so that's, just to be precise, that's this formula where I did all this by paper and pencil. Now let me use this formula where I actually measure using the hardware performance counters, how much traffic there was, and I get that line. So this is lower. It's pretty close, but it follows kind of the same trend. So it's lower because it actually did more memory traffic than my paper and pencil lower bound on memory traffic, but you know, it's not so far off. And finally, here is the actual measured data. This is the actual speed that was attained. And again, the trend kind of follows. For these finite element matrices with single blocks, I'm getting anywhere from 2/3 to 80% of this peak performance. And then down here, it gets a little bit worse. So this is sort of telling us that we're doing we have a reasonable hardware understanding of what's going on, but it's not perfect. But you know, we're getting anywhere from 2/3 to 80% of peak. So that's how you tell whether you win or not in this business. So all of that was for one optimization. There are a lot of optimizations. And so here is a table of some other sequential optimizations. You know, forget the parallel, right? I mean, we'll get to that later, like graph partitioning. This is all just sequential optimizations. And I've just spent you all this time talking about one of them called register blocking, picking those little R by C blocks. And we saw that, at least in one case, we got over a factor of 4 over the naive compressed sparse row format, 1-by-1 blocks. But there are a lot of other optimizations. Let me just outline them. So you could decide that instead of choosing one block size, I'm going to break my matrix up into separate matrices and use a different block size for each one. That's a perfectly natural thing to do. That can get you up to a factor of 1.8 over choosing a single block size, depending on what your matrix looks like. Some matrices naturally come in diagonals. In other words, if you look at their SPI plots, they look like, you know, diagonals going down. And a perfectly natural data structure is to store the diagonal as an array and just remember, am I on the first diagonal or the third diagonal, and use that as your data structure. That can sometimes, for some sparse matrices, give you a factor of 2 over the naive format. So sometimes your matrix, you look at it, you zoom in, and there's no dense blocks whatsoever. But if you were to reorder the rows and columns, so just permute the rows and columns, then you can push all the non-zeros closer together. I'll show you an example. And you can create dense problems where they weren't there before. So instead of doing matrix vector multiply with your original matrix, you're doing it with a permuted matrix. Now that changes your higher level algorithm, but sometimes that doesn't hurt you at all. But you have to think about how to do that. And that can also give you a factor of 2. If your matrix is symmetric, it's obvious you're only going to store half of it, and maybe the upper triangle, and use that twice. That doubles your memory usage. Excuse me, it doubles your computational intensity. And that you'd expect to give you a factor of just 2, but you can actually get a factor of like 2.6 because, again, of the idiosyncrasies of how the hardware works. So all of that is blocking at the register level. You can also have cache blocking. And why would you do that? If your vector x is so big it doesn't fit in the cache, well, you break your matrix up into rectangular blocks so that you only need a part of x chosen so that it fits in cache. That can give you a factor of 2.8. And there are a lot of algorithms where you're not just doing a single sparse matrix vector multiply, but you have lots of vectors. And if you have all those vectors at one time, then there's obviously reuse that is beginning to feel like sparse matrix multiply, and that can give you up to a very large factor of 7. And you can have arbitrary combinations of these, right? All of these are possible, and that's why you want a tool like OSCE that tries them all in whatever combinations make sense and does it for you. So this is all just sparse matrix vector multiply. There's also solving triangular systems. These optimizations also work in that case. You can get a factor of 1.8. And then the real payoff, which we'll spend most of the next lecture on, is for higher level kernels. So it turns out in a lot of algorithms, for example, for the singular value decomposition, you're not just multiplying by A, you're also multiplying by A transpose. In fact, you're multiplying A transpose times A times X. And it turns out you can read A from memory once and do both of these matrix vector multiplies. You can do twice the flops for the same memory traffic if you reorganize things appropriately. And this pattern actually goes up to using it k times over and over again. And we'll talk about that next time. So let me just show you a few more pictures of a couple of these, and then much of that will be left to next time. So let me mention about sparse triangular solve. And so here is a SPI plot of a typical sparse matrix. It comes from doing sparse Gaussian elimination. And if you remember how Gaussian elimination works, you're taking multiples of one row, adding it to the next row. you keep filling in the matrix every time you do that. You keep adding new non-zeros, and so the matrix keeps getting denser and denser as you get to the bottom corner. And it's not unusual for the matrix to become completely dense once you get to the bottom corner. So in this particular case, 20% of the non-zeros of this sparse triangular matrix are sitting down here. And so at that point, you might as well say, I'm not sparse anymore, I'm dense. I'm going to switch to a dense format and use the optimized BLAS at that point. And that can get you a factor of 1.8. Okay? So one more example. I think I have time for this. How do you optimize A times A transpose times X? This was the example I said that's the inner loop of a lot of algorithms, like for the singular value decomposition. Well, what you can notice is, let me write my matrix A column by column. So little a1 is the first column and so forth. And so the first row of A transpose is A1 transpose. And let me just reorganize the algebra so it looks like this. So what does this say? That means that what I'm going to do is I'm going to read in the first column I equals 1 of A, and I'm going to do a dot product and keep it in memory. And then I'm going to take that scalar and I'll do an AXB with that. So I get to use this first column of A twice, even though I've only read it once. And then I'll do it for A2 and A3 and A4, and so I get twice as much reuse as I normally would. And at the register level, of course, this wouldn't be a single column. This would be, maybe R columns, or excuse me, C columns. Okay. Then I have to get to combine things. And so let's suppose that I want to do sparse matrix multiply. So what I want to do is I want to take advantage of the fact that my matrix is symmetric. So I'm not going to store this stuff down here. I'm just going to store the upper triangle. I want to take advantage of the fact that I'm going to do register blocking. And I'm going to take advantage of the fact that I'm not going to do a single vector x. I'm going to have k vectors x. So I now have 3 blocking parameters that I have to pick. I have to pick r, I have to pick c, and I have to pick how many vectors I'm going to do at the same time. So the question is, what is the payoff for doing this? And I think I will stop after this slide. So this was work done by an undergrad here, who's now an assistant professor at Duke, Ben Lee. And so if you compare to the non-symmetric code, but you do the register blocking, and you have one vector, and you change it to being symmetric, that's the only optimization you do, then you get a factor of 2.6. So now, let's suppose that I start with the non-symmetric, non-blocked, one vector code, and I take advantage of everything. The fact that it's symmetric, and it's blocked, and it's k vectors. All 3 of the optimizations of the previous slide. There's a factor of 7.3 speed up. That's worth taking advantage of. So all of these combinations are worth doing. And next time when we come back, we'll optimize the higher level optimizations where I'm doing many sparse matrix vector multiplies. Okay, we'll stop here.